Okay, so first thing first, this is the last class before spring break. Yay. But I have homework for you. Oh. I don't think it's going to be taking a whole lot of time. Yep.
We don't have class on Thursday?
We do have class on Thursday.
So this is not
For
the
as
last
far as
class?
this class is concerned, this is the last class before spring break.
So
if you have classes on Thursdays, those will be tomorrow.
this class will not be on
Today is a
Tuesday.
okay, so we do have a class on Thursday. Okay, sorry, I forgot. Okay, I thought today was a Wednesday. Okay, never mind. So we do meet on Thursday. So darn.
You wondering why no one showed up for class next Thursday?
That would be kind of funny. Yep. Okay, but we do have a homework assignment. But this is even better because it gives you a chance to get it all done before you start your spring break. Okay, so that would be nice. You can get everything done, and then you don't have to worry about it in spring break. Okay, so this is the homework assignment. I don't want to use any existing Lotto games because you can easily look up information. So I'm gonna do this kind of like a make-up Lotto game. But this is also a little bit simplified, so it does make the modeling a little bit easier. Okay, so this is my own Lotto game because I have to raise money for my own kids to go to college. Okay, so ask your parents. Okay, are they running some kind of Lotto game in a foreign country just so that you can go to college at some point? Okay, so with the emphasis where it is legal. Okay. And this is the game, how the game is played. So I would issue unique Lotto tickets. Each ticket can only be sold to one person. Now that is a big change from the usual Lotto game because in the Lotto game, most of the time they can sell duplicate tickets or tickets with duplicate numbers to multiple people. Okay, that's what happens with the usual Lotto game in California. This gives you a pretty good constraint, of how you can analyze the problem. Okay, because for each unique sequence and combination, you can only have one single ticket. Okay. On the other hand, okay, let me get through this part first. Each Lotto ticket costs $1. Okay, it's just a unit of how much it costs. A person can purchase any number of tickets. It's not really particularly useful, okay, but it's part of the rule. Okay, anyone can buy any number of tickets. And this is the important part. The Lotto drawing, okay, on every Sunday this happens. Out of a tumbling bucket, someone is going to pick out 6 out of 30 balls, and then these balls are all labeled from 1 to 30. So I would put 30 balls, labeled 1 to 30, into a tumbling bucket, and then somebody's going to pick out these balls one by one, and 6 of these balls will be picked out. So that would be the first part of the drawing. The second part of the drawing, which is this part here, is I will also use in a different bucket, okay, different tumbling bucket. I would put in 3 colored balls, okay, red, green, and blue. And those 3 will be picked out of that tumbling bucket. So 3 all out of 3 will be picked out. But in this case, the ordering is important. Okay, is it in the order of RGB? Is it in the order of RBG, BRG, or whatnot? Okay, so that part becomes important. Okay. All right. So the first part, where the numbers are concerned, as far as the numbers are concerned, the ordering is not important. But with the color ones, it is important. Anyone who has 4 out of 6 matching numbers in any sequence is going to win $10. Okay, that's the lowest price people can win. If the ordering of the color balls are also matching, then the prize money increases to $50. I'm missing a 0 here. I will fix it right now, just so that I don't forget to do it. So hold on 1 second. Let me fix that. Because I changed the winning amount from $1 to $10, so I have to match the other number. So matching this one to 50. So let me save it first. Hold on 1 second. There we go. All right. So if the ordering of the color balls are also is also matching, then the prize money increases to $50. It's not $50 in addition to the $10. It is just $50 for that one single ticket. Are there any questions about how to win $10 and how to win $50? Yep.
Are the balls that are numbered 1 through 30 colored or no?
No, the numbered balls are not colored. So there are two buckets. One bucket with numbers and one bucket with colors.
And so the player would pick a lottery ticket and it would have both a number and a color scheme?
Yes. So you would pick the numbers, and on the ticket, the numbers would be sorted, okay? So it would be 1, 10, 11, 23, 25, and then 30, okay? So there are 6 numbers here. And then you have to pick the color sequence. So the color is going to be a sequence, so I can pick green, red, and blue. So this one, the ordering does matter because I will pick all 3 balls out of that bucket. Whereas in this case, the ordering does not matter, okay? Because I will pick 6 numbers, but before I announce the winning number, it will be sorted. Okay, and on each ticket, these numbers will be sorted as well. So to win $10, okay? To win $10, that means out of these 6 numbers, 4 has to match. Okay, exactly 4 has to match to win $10, and then the color sequence is not matching. If you have 4 out of 6 numbers matching, and the color sequence is also matching, then you get $50. Is that okay so far? All right, so the second one is if someone is luckier and get 5 out of the 6 numbers matching in any sequence. Okay, so it can be any 5 of the 6 numbers. In other words, if anyone that has that has picked the numbers 1, 10, 11, 23, and 30 will win $1,000, assuming the color sequence is incorrect. Okay, so there are several ways to win the $1,000 range. Is that okay so far? And in the case of matching exactly 5 out of the 6 numbers, in addition to that, if the color combination or the color sequence is also matching, then the prize money goes up to $5,000. All right? Is that, yep?
So your chance of getting colors sorted is not going to change. But your chance of getting your colors sorted, you have like 3 balls, and those colors, if you get them right, then your chance is the same as the step before. The only difference is now you have 5 out of 6, right?
Okay, so let's say this is the actual winning draw, okay? So if my ticket is like this, if my ticket is 1, 5, 10, 11, 23, and 25, and my color sequence, the color sequence that I pick is just RGB, then this is a $1,000 win. Okay, because my color combination is not matching, but 5 of my number is matching the winning number. Okay? Is that making any sense? Now, on the other hand, if I pick the colors also correctly in the right sequence, then I win $5,000.
No, my question was that your chance of getting it right for the color side, same both steps. Either you get 4 or 5. There is just 1.
Correct, because this is coming from a different bucket altogether. All right, so anyone who has all 6 matching numbers will win $100,000. If someone has the 6 matching colors and also have the right ordering of the color balls, then the jackpot is won. Okay? Are there any questions about the 6 ways of winning in this case? Okay. Now I do make it a little bit easier for you guys to analyze because I said there will be unique tickets. Okay, I'm not going to issue the same combination of numbers and sequence of colors twice. Okay, each one will only be printed exactly once. So there's no way you can have 2 people with the same ticket. Are we doing okay so far? And if you look at the way I specify the jackpot, there can only be one person winning the jackpot. With the other type of winning, there might be multiple people, but with the jackpot, there can only be one. Is that okay?
There is just one person who has green, red, and blue.
There can only be one person with the right color sequence on top of the right number combination. Is that making any sense? Yep.
So if your number sequence doesn't match, but you do get a matching color sequence, it doesn't matter?
It doesn't mean anything. Yep. Okay. Is that all right? Yep.
You want us to do it on the editor, or can we just do it on paper and scan the paper?
Do it on a piece of napkin and then do the high-tech thing of using a cell phone to take a picture and then turn it in, right? I suppose it's going to be okay, but I have to open it up for attachments. Because right now, you can only do the online editing. Yep.
Is there any way that you can show us like what the first line of the proof might look like?
The first line of proof?
Just like the first line.
What you want to do, okay, let me explain the full homework assignment first, and then I can give you some, it has some instruction of how helping you out. Okay, so given these are the rules and not counting the jackpot, on the average, is this game even sane? In other words, am I going to lose money or win money in the long run? On the average, okay, this is just according to statistics. Is this a game, and I set it up so that I will be the one actually losing money in the long run, or am I going to win money in the long run? Okay, and I don't know. I really do not know the answer to that question. I just set up these rules, and I go like, well, we'll just run with that, and then you guys will have to prove whether I'm going to win money or not. So what you need to do is to prove it. Now to prove this, what you want to do is to make the assumption that all tickets are actually sold. So you have to first calculate how many possible unique tickets I can actually issue in this case. Okay? So out of that many tickets, let's assume that I sold every single one of them. Okay? So every single one is sold. That makes it very easy to model, whether this is a winning game or a losing game from my perspective, because each ticket is only costing $1, right? So if you know the number of tickets that I can possibly print out, because they all have to be unique and they're all sold, you know how much money I have incoming, okay? And you don't have to worry about taxing and stuff like that. I know we're close to tax day, so you or your parents may be doing all the taxes, but in this case, let's not worry about taxing, okay? So there's no taxing involved. But then you will also find out, based on the rules, you can also find out exactly how many people will be winning $10, how many people will be winning $50, how many people will be winning $1,000, $5,000, and $100,000. Okay, and I'm not going to include a jackpot in this case because the jackpot has to do with how much money was left over from the previous time. Okay. Yep.
How many tickets were sold?
It's all the tickets. So assume all possible tickets are actually sold.
Of all the combinations.
Of all the unique tickets, and for each unique number combination and color sequence, there's only one ticket, right? So that makes it easy to analyze how many possible tickets can I possibly sell, and then each one is $1. So you know how much money will be incoming. But by calculating how much money I'm paying off, how many $10 prices I'm paying, how many $50 prices I'm paying, and so on, we can come up with a number and say, okay, if all tickets are actually sold and everybody is collecting their prices, this is how much money I have to pay off, guaranteed. Okay. The jackpot is a different story because it is based on the leftover, cumulative leftover from previous times. So that's why in this calculation, you don't have to factor in the jackpot.
What is the range of numbers again?
Say again?
What is the range of numbers again? From 1 to 30?
1 to 30. The numbers only go from 1 to 30. So right here, okay? So the numbers are going from 1 to 30, and I will draw 6 out of the 30 balls. Okay? All right? So and then the second question, that's the first question, am I winning or losing in the long run? And then the second question is, what are the chances of winning the jackpot? Okay, and you express your answer in the form of 1 out of how many, chances on the average. Show all steps and explain your reasoning in your proofs. Personally, I think it is best to use a spreadsheet to work on this one, because if you know the spreadsheet, formulae, you can easily set it up to handle like multiple cases, and there's a lot of similarity between the prices. So if you set up a spreadsheet, it makes it so much easier. You can always type in comments in the spreadsheet. So once I open up attachment as a possibility to turn in your homework, that's one way to do it. Okay, you can always do it on a piece of napkin too, using ketchup and mustard. Mustard is good for highlighting, and then ketchup is good for writing. And since I don't have any color blind conditions, you can use any color of ketchup and I will still be able to read it. Unless it's the same color as the napkin itself, then it becomes kind of difficult. Any questions about that? No questions? You guys all thinking, okay, so which napkin should I use? Which restaurant am I going to go to get this homework assignment done? All right. So I don't think it would take you a lot of time to do this. Okay, once you understand the homework assignment, and once you understand what is a combination as opposed to what is a permutation, okay, this won't take you too long. Yep.
You said that the ordering of the numbers didn't matter, right?
Correct.
Okay.
Yep. All right, so that's your homework assignment. We are meeting on Thursday. Okay, let me just reconfirm that we are meeting on Thursday. If you have any questions about the homework assignment, bring it on Thursday and we can talk about it. You can basically bring in a scenario and go like, okay, this is the way the balls are drawn from the 2 tumbling buckets, and this is the number. What am I going to win with this number? That would be a good question to ask, in case you have that kind of question. All right. So given that is done, we'll kind of move forward and talk about discrete probability distribution. And we'll start to get into Pascal's identity and also the binomial theorem. I'm not going to give you guys a whole lot of homework assignments as far as proving these 2 theorems are concerned, because they're all over the internet. Okay, if you just type up Pascal's identity, like 20 pages of different proofs. The binomial theorem, same thing. Okay, so these are well established theorems and with proofs all over the place, which you think will make my job a whole lot easier, right? I just have to point you to a Wikipedia page and be done with it. Well, that's not what I did. I actually went ahead and proved these theorems without looking up on the internet, because otherwise, what would be the fun of teaching this class? I mean, this is the only way I can be sure that I can actually teach you the material, because otherwise I would just be pointing to a wiki page and say, read that wiki page, and I'll just be doing my stuff over here while you guys are just reading the page and go like, Tag, can you scroll down a little bit? We're done with this page. Okay, scroll down, and then I go back and do my own thing, right? But this kind of brings up an interesting question. How many of you have taken a online class in programming or in any type of subject matter? Okay, so as far as you are concerned, or as far as your assessment is concerned, do you get the same amount of instructor interaction with an online class? No. It's not equivalent to a face-to-face class. Now, how is it not equivalent?
Keep ask questions for one.
But you can send an email, right? I mean,
and wait a day or 2 for it to come back.
well, it cannot be more than a day. I think there's a certain limitation of how quickly they have to come back to you. Yep.
Well, if you go to the office hours, it's pretty similar.
Okay.
And then you still get that face-to-face interaction.
Right. How about reminding you about homework assignments or things that will be happening, asking about, prompting you and say, oh, do you have any questions about whatever, right? Something that we talked about last time and stuff like that. Would that be, is there an equivalence with online classes? Your instructors did not send email regularly to you and say, just sending out a reminder that we have a homework assignment due in 5 days. Do you guys have any questions about it?
Email warns you for like you said that email thing. So it will send you an email saying like you have this homework due, you don't check it.
Okay, so you can set up on your end, or the instructor has to set up on his own?
I guess you set it up on your own. You can open it.
Okay. What about when you're not doing so well and your instructor sends you an email and go like, well, you might want to review this material, or I noticed that your score is not exactly encouraging at this point, or something like that. Not much. Not that I do it in this a face-to-face class either, because there are 50 of you.
It's more of like a book based.
Okay.
You read the book, you do the material fine. If you don't read the book, you can't do it.
Okay, the reason why I'm asking is because the college district as a whole is trying to emphasize on the REC, and you might hear this term, again. It's called regular effective contact, which is also called RSI, which is regular substantive interaction, which is supposed to be initiated by an instructor in an online class to be basically doing the same thing as what I did. Okay, asking you, do you have any questions about the past material, or if there's a homework assignment that is assigned, I will remind you and say, well, next Tuesday we have a homework assignment due. Do you have any questions? Have you gotten started yet? So that's kind of the thing that the college district is trying to do to make online classes more equivalent to their face-to-face version. Okay, so kind of keep that in mind, because you might actually see surveys regarding that, especially in the fall, because in the fall the entire college district is getting accredited in the fall. So there will be people coming on campus to assess how we are teaching classes and stuff like that. And that will be, I think, one of the focus areas. All right. One of the things, as far as I'm concerned, one of the things about online classes is the expectations from students may be different compared to a face-to-face class. For instance, for a class like this, okay, so let's say I give you a homework assignment. It's much more difficult or much more vague or ambiguous than the one that you just saw, okay? So many of you are raising a hand, you're frowning and trying to ask me questions to clarify what the homework assignment is asking. If I give you a blank look and completely ignore all the hands and all the people who are asking the questions, you guys would go like, what's up with Tack? He's not answering my questions. Because I normally would answer a question with more questions, at least it's an answer, right? But if I'm not even addressing your question, then some of you may, and legitimately so, feel that, hey, this is not how a class should be taught. And you walk to my dean, walk up to the dean and ask him and tell him about this and go like, is this normal? Am I supposed to, take a class like this? But with online classes, the expectation may not be the same. So I think that's the main difference between a face-to-face and an online class is the expectation from your perspective is also a little bit different, because you may not know what you should be expecting. And the general idea is you should expect the same type of interaction from the instructor, even though it is online. All right, well, getting back to the good stuff here. Okay, the good stuff is Pascal's identity is basically this particular statement. For all k from 1 to n minus 1, and the entry of Pascal's identity on Wikipedia has it wrong. It actually has a wrong. There's something incorrect about that one. I'll let you guys find out what is wrong with it. It's not a homework assignment, but for those of you who want to look it up, there's something wrong with the Wikipedia entry. Okay, so basically, if you pick a k so that k is from 1 to n minus 1, this has to be true. This equality has to be true. So in other words, the combination of picking k things out of n plus the number of combination picking k minus 1 things out of n will be the same as picking k things out of n plus 1 things. Okay, so to give you a concrete example, there's one right next to it, but I can give you another one. Okay, so let's say we're dealing with 15 and oops. It's probably better off just to do it here. I know what. I'll use a LibreOffice, using a spreadsheet. This will be really beneficial because it will also help illustrate some of the functions you can utilize when you're doing your homework assignment. So let's go ahead and start a new spreadsheet. So let's say n is, I don't know, 15, and let's say k is 5. Okay, and I will change this to so I can display both the theorem and the spreadsheet at the same time. There we go. Sort of getting there. There we go. So I want to show you, what is the number of combinations if you are to pick k things out of n. In this case, k is 5 and n is 15. Using a spreadsheet, that's pretty easy. Okay, using a spreadsheet, the number of combinations of picking 5 out of 15 things is the following. Okay, so use an equal symbol to start a formula, and it's just a combination. So if you type combin, okay, without the whole name, use open parentheses. The first number is 15, which is the total number of things that you're picking from. And then the second number is 5, which is the number of items that you're picking out of 15. It's that easy. Press the Enter key, and it is 3003. Okay, and I'm just suspecting, okay, not saying that for sure this is going to help you with your homework assignment, but I have a strong suspicion that this might be helpful. Okay. All right, the second one is C15, which because n is 15, but k minus 1 means it is picking 4 items. And the same thing, I'm going to use combin, and we're picking 15 things. Out of 15 things, we're picking 4, and the answer is 1,365. And these two numbers seem pretty kind of random. Okay, they don't seem like they're related in any way. And this time, I want to look at the right-hand side of the equality. And I say, well, how about this number? Well, first of all, let's do the total here. So the total is this number plus this number here, and it is 4,368. So now we want to look at the combination of, out of 16 items, we are picking 5. And we want to do the calculation here, and it is combin 16, 5. And they match up. Okay, so magically, this equation seems to work out, at least for this particular case. Now, if you look at the way Pascal's identity is set up, it is actually also matching the Pascal's triangle geometry. Okay, I'm just going to redo the Pascal's triangle in case somebody missed it last time. So 1, 1, 1. Then we have 1, 2, 1, 1, 3, 3, 1. And then we have 1, 4, 6, 4, 1, and so on. So what we are looking at is adding these two numbers to come up with this one. Are we doing okay so far? So on the next row, we have 1, 5, 10, 10, 5, 1. We're adding 4 and 6 to become 10. This 4 is picking k minus 1 out of n. This one is picking k out of n. This one is picking k out of n plus 1. Okay? So when you look at Pascal's identity, it does have a strong relationship with Pascal's triangle because it is expressing how you get to the next row from one row in Pascal's triangle. Are we doing okay so far with this? Are there any questions about the relationship between Pascal's identity and Pascal's triangle? This is Pascal's triangle. Yep.
N is the depth and K is the column?
Correct. Well, sort of. It's the number, on the row. And either one can start with 0. All right. So how do we prove it? Okay, just because it works for this particular case, when n is 15 and k is 5, is not sufficient reason for me to believe this is a general theorem. Okay, it works in one case. Okay, so what we'll do is we'll go through the proof. Instead of reading the proof to you, okay, I want you to kind of think about how are we going to prove this. What do you think? This one, sorry, go ahead. We can use special properties of factorial to do it. Okay, so we'll go ahead and expose maybe just a little bit here. Well, not exactly factorial. Well, it is factorial, but we're expanding the number of combinations to factorial, a fraction involving the use of factorial. Okay. Instead of just reading out the notes, well, it's kind of hard to do it, because there's a lot of typesetting, so I don't want to really do it, live in the class, because that is going to take up a lot of time. So what I'll do is I'm going to, okay, I can show it row by row, and for people in the back, it's a little bit hard to read, so I'll readjust the screen a little bit so that we can do it this way. Continue with scrolling. There we go. Okay. So if you look at the bottom row here, okay, this is just expanding the number of combinations into a fraction involving factorial, which is pretty much by definition. Are there any questions about how I expanded the number of combinations? And picking k out of n is re-expressed as this particular fraction here. Cannot highlight it. There we go. Is that part okay? We kind of talked about this last time. We talked about how to calculate the number of combinations. Is everybody somewhat comfortable with this? Okay. Question?
So
Yep.
only step you change the combination sign to the factorial sign.
This is step one. Okay, so step one is just doing that. Then you look at the second term of the addition, which is picking k minus 1 item out of n, and that is now re-expressed as this portion here. But it's still doing the same thing. I'm just reapplying the same equation. Are we doing okay so far with this? Okay. So in the next step, what we do is we arrange things a little bit, just a little bit, not by much. Okay. So this is the next step. So you can see in the next step, there's not really a whole lot of change. All I did is to rearrange n minus open paren k minus 1 close paren to n minus k in parentheses plus 1. Is that okay? In other words, it's only this part that I made some minor changes. I took this expression. This wireless mouse is not cooperating. Do you think I might get a gaming mouse if I ask my dean to buy one and say this mouse is not good enough? It doesn't have 1600 DPI, and I need that to teach a class. And then Walter would come in and say, but Tag, how come that mouse is always missing over the weekend? Okay, back to a wired mouse. Okay, much better actually. Okay, so I'm talking about this expression, which is n minus, and then in parentheses k minus 1, and I just change it to n minus k in parentheses plus 1. And that's just by using the associative law of addition. That's pretty much it. Are we okay with this step? Okay, pretty simple step. It's simple, but it's also very important. So in the next step, okay, let me scroll down a little bit here. So in the next step, I multiply k to the second term on both the numerator and the denominator. Okay, but this step may not look intuitive. Okay, so going from the second row to the third row is a little bit tricky. The top part is easy. The numerator, because I'm just multiplying k over k to the entire fraction, so the numerator has one extra term k, so it is n factorial k. That's easy. But what happens when I multiply k to k minus 1 factorial? If I multiply k to k minus 1 factorial, I get, well, guess what? K factorial. And that's what happens here. So the k factorial is absorbing the extra k that I multiply to the denominator. Are we doing okay so far with the second row to the third row, the transition between these two? Okay. And then after this, what we do is this one here. Okay. So in this particular step, I'm transforming the n minus k plus 1 factorial to just n minus k factorial by dividing n minus k plus 1 from both the numerator and the denominator. Is that okay? So I'm dividing n minus k plus 1 from both the numerator and the denominator of the second term of the addition. But what happens is, it will simplify this term. If I divide this term by n minus k plus 1, I end up with just n minus k factorial. But on the numerator, there's nothing that I can use to simplify, so I would end up with a fraction or with a denominator on the numerator side. Are we still doing okay so far with this? Okay. Okay, so going from here to the next step, I try to, and you can see how the denominator are now the same. Okay, the first term has this particular denominator, and then the second term has the same denominator. So now I can try to combine these two terms, but when I try to combine these two terms, I have to make sure the numerator are also matching. So this is the next step. I know this is getting a little hard to read because they're kind of squished together. Okay, so for this time, we have to kind of focus on this side. When you look at this portion here, okay. That's really just n factorial, because I just multiplied both the numerator and the denominator by n minus k plus 1. That's all I did. But now, when you look at the numerator of the first term and the numerator of the second term, they do have a common denominator now, which is n minus k plus 1, n minus k plus 1. So now I can just freely add these two. So in the next step, right here, I combine the numerators of the two terms, and we have a denominator for the numerator part, and then we have the final denominator here. But that's just kind of redundant because I can now absorb the n minus k plus 1 into the actual denominator. What happens when I multiply n minus k factorial to n minus k plus 1? What do I get? N minus k plus 1 factorial, which is also known as n minus, in parentheses, k minus 1, close parentheses, factorial, right? Okay, so that's exactly what I did in the next step. Well, okay, this is an intermediate step by just copying this portion over here and then combining the two denominators. Okay, but after I combine the two denominators, I get this one here. I forgot one factorial, didn't I? Yep, I did. I forgot a factorial here. I'm thinking about whether I should fix it now or not. I really should fix it now, because if I don't do it, I will forget to do it later. So if you guys just give me a moment, I'll go ahead and fix it. I'll fix it in another slide here. So this way I'm not losing my spot in the original text. This may be actually beneficial too for those of you who want to see how all of these equations are actually handled, and you get all typeset kind of nicely. In its raw format, this is what we see right here. And I have to find the right spot to fix. I think it's this one here. I used to type LaTeX, with all my notes, so this is actually something that I'm pretty used to. Now this should be fixed, and I just have to refresh this one. I think after I refresh, it will keep the same spot. Yep, it did. And you can see this, the factorial is here. Are there any questions about this particular step? I'm just absorbing the extra term n minus k plus 1 into n minus k factorial, so I end up with n minus k plus 1 factorial. So from here, we move on to the next step, which is just a slight rearrangement so that we have the plus 1 next to the n and then the minus k at the end. Okay, so we are just using the commutative law of addition. Okay, so you see how what the change is? It went from n minus k plus 1 to n minus 1 and then n plus 1 and then minus k. Is that okay so far? Well, why do I group these terms in this particular way? Because I want n minus 1 to be together, and then I want k to be a separate term. Because when you look at this, what is the other way to express this particular fraction? It's the number of combinations of picking k out of n plus 1. Exactly. Because it falls into that particular format, and now we have the conclusion. That's the proof. Are we okay with this? There might be a faster way to do it, because I did not actually look up on the internet of how to do it. I just did it myself, which may or may not be the quickest way, but it is one way to do it. And all I did was to make use of properties of factorial and just basic rules like associative rule, commutative rule, and distributive rule of arithmetics. Are there any questions about this kind of proof? If I were to ask you, is this a direct proof or is it an indirect proof, which one do you think it is? It's a direct proof. Yep. Cool. So what this is, okay, what Pascal's identity is doing is it is going to serve as an intermediate step, okay, to the next theorem. Okay, the proof of the next theorem is going to make use of Pascal's identity. We still doing okay so far? Okay. So the next one is called the Binomial Theorem. So we'll go ahead and move on to the Binomial Theorem. And once again, you can look it up online. Okay, you can look it up on Wikipedia, and the whole proof is on Wikipedia already. Yep.
Actually, could you go back to Pascal, the last line? I didn't quite understand that.
Okay, sure. Give me this one.
Yeah, the transformation of k.
Okay.
N plus 1 minus k.
If you consider n plus 1 as a new term, let's call that m, okay? So this is m here, and this is m as well. So now you have something that looks like m factorial as a numerator, and then the denominator is now k factorial m minus k factorial. So by the definition of the number of combinations, this is really the same thing as m pick k out of m items, the number of combinations. But as it turns out, because of the way I group items, in this case, m is just n plus 1. So that's why I group n plus 1 as one single term, and so that I can use this format to link it back to the binomial term. Yep.
Are you missing an exclamation point from the
What up for K?
Am I missing an exclamation point from k, right, this time?
Yes.
This k here?
Yeah.
Mhm.
Yep, I did. You got me. I had to jump between the preview mode and the edit mode quite a few times for this one, because when you look at this, even though I'm used to it, it's still pretty hard to spot the missing exclamation point, which is right here. Save. Okay, there we go. Let me get back to the page and see if you guys have any more questions about it. Any more questions about Pascal's identity? I apologize for the mistakes. So it's all fixed now. There we go. questions? Okay, let me pose this question then. If I don't want you to look up online, okay, so let's say we do it, you know, as a in-class exercise. How many of you feel confident that you can get it done, not necessarily in the amount of time that took me, okay, you know, say about half an hour? Do you guys feel confident that you'll be able to prove the identity? Sort of. How is it? Is it about the same, or is it really different from the math from the other classes? Pre-calc or calculus?
It's about the same.
About the same, right? It's still about, you know, the manipulation of symbols. And in this case, there's no such thing as, you know, taking the limit of something, you know, or special things you have to remember with integration and differentiation. This one is really just arithmetic for the most part. The trick is to combine terms like this, okay? The trick to this one is to combine k plus 1 times k factorial to k plus 1 factorial. This is the trick. That is not in quote-unquote normal math. But once you understand this particular trick, this proof is, well, fairly easy, fairly straightforward. This is the only part that is missing from what we already know about multiplication and stuff. All right. Yep, go ahead.
What does that mean again? That equals m and parentheses m over k again? Like, what does that represent?
It is also written in this way. Okay, if you use a big C, then you have an m on the top and a k at the bottom. It means this is the number of combinations of picking k items out of m.
Gotcha.
And if the C is a P, then it becomes the number of permutations of picking k things out of m. Permutations is when the ordering is significant, and combinations means, you know, the ordering is not significant.
Gotcha. Thank you.
All right. Shall we move on? Okay. So the next slide is about the binomial theorem. And the binomial theorem is obviously something that is well known, well studied, and also well documented along with its proof. Okay, so when you look up the proof, you know, it's no big deal. And I forgot one close parenthesis this time because there's one open here and it's missing an end. It's also the wrong size. So let me fix that first. So we'll go ahead and fix that. And right here. And to make this one look right, okay, the parenthesis cannot be just a parenthesis. This one has to be named a left open parenthesis, and it has to be matched by a right close parenthesis. And this will make it look right. It will make the parenthesis look a lot bigger, and it will basically match the sizes that we need here. So let me just refresh it. And there we go. All right, so this is the binomial theorem. It basically says if you have 1 plus x to the power of n, okay, you can re-express the same product, but in the term of the summation of I going from 0 to n, and then for each power of x, the power or the coefficient is n choose I, okay? Well, let's check this out and see if it makes any sense. Okay, so we'll work out, you know, maybe the first 2 or 3 cases, just to make sure that it does make sense. I'm going to do this on the whiteboard because it's really a quick check. Okay, let's take a look at to the power of 0. Okay, 1 plus x to the power of 0 is what? It has to be 1. Okay, can I say that 1 is x to the power of 0? So in this case, I am choosing 0 out of 0 things times x to the power of 0. So the theorem is holding true. Is that making any sense? Is everybody comfortable with the summation operator? It's basically just a big, huge addition where the term I goes from 0 to n. Let's take a look at what if the power is 1. And that would just be 1 plus x, right? But when you use the summation operator, it becomes 1 choose 0 of x to the power of 0 plus 1 choose 1 times x to the power of 1. Is that okay? In other words, I'm just expanding the summation term. What is 1 choose 0? How many ways can you choose 0 things out of one item? It's 1, right? So this is 1 times 1, which is, because x to the power of 0 is just 1. How many ways can you pick one thing out of one thing? One way. And this time it is the coefficient of just x. So we get 1 plus x back. It does work. Okay. We'll try one more time, okay, just to see that it also works for the square. 1 plus x squared. Okay. This one we already know because we have taken a lot of classes with stuff like that. So plus 2x plus x squared. Okay. But does it work? Okay. Let's go ahead and say we're choosing 0 things out of 2 things, and that would be the coefficient of x to the power of 0. We're choosing 1 thing out of 2, and that would be times x to the power of 1. And then we have the last term, which is choosing 2 things out of 2 things, and that will be the coefficient of x squared. Is it working out? There's only one way to choose 0 things out of 2 things. So the first term is just 1 itself. The second term is there are 2 things to choose 2 things. That there are 2 ways to choose 1 thing out of 2, so it becomes 2x. And there's only 1 thing to choose 2 things out of 2 because the ordering is not important. So it becomes just x squared, and it works out as well. All right? So this is just an example to illustrate what the theorem is trying to say. But what it's trying to say is it's not just working for the case when we're dealing with to the power of 0, to the power of 1, or to the power of 2. It is for all natural numbers n. So the question now is, can I illustrate that it is true for all cases where n is a natural number? 1 plus x to the power of n is the summation of I going from 0 to n choose I times x to the power of I. What do you think? Well, since it is a theorem, it obviously has to be true. But how are we going to prove this? So what we'll do this time is we're going to introduce a new technique of proving. It is called proof by induction. And I'm not going to explain proof by induction until the proof itself is over. Then we'll go back and kind of look at proof by induction in general. The first paragraph says intuitively, this theorem makes sense. Now, the way it makes sense is when you have 1 times x n times, okay, there are obviously, and you want to worry about x to the power of k, then there are k terms that will contribute the x, and then there will be n minus k terms that will contribute a 1, and therefore you end up with x to the power of k. But the number of ways you can combine between all the individual terms should match also the number of combinations. So intuitively, it does make sense, but just because it makes sense intuitively doesn't mean that it is a proof, right? It doesn't mean that it has to be true. So just because something is intuitively true to one person does not make it true, at least not in math. Okay, in some other classes, in some other disciplines, that may be true, but not in a math class, nor in computer science. So what we want to do is we want to prove it using a rigid mathematical proof, and this time we'll do it by induction. Now, when you prove something by induction, it's interesting because it has a strong correlation with a particular style of programming, which is How do you write programs without loops?
Recursion.
By recursion, okay? So when you have recursion, it is kind of a similar thing, okay? Because you are relying on one step to move on to the next step, and proof by induction is the same way. So proof by induction requires that you have to establish what we call a base case. A base case is kind of the same thing as in a recursive algorithm, the case where you do not call the subroutine again. Okay. In the case of factorial, for instance, if you look at factorial in the recursive way, so we have int f of n. Okay, how would you write it? Okay, I'll spell out the long way. Okay, this is the long way to do it. So if n is greater than 0, then we return n times f of n minus 1, else we return 1. That's one way to write a recursion, a recursive version of factorial. So in this case, which one is my base case? Which condition says there's no need to do any further recursion? When n equals to 0, right? Okay, so that's the point when I stop the recursion. So the point where you stop recursion is kind of the same thing as a base case in proof by induction. That's when you say, okay, we know this one for sure. Okay, the other ones, maybe not so much, but this one we know for sure. So in this case, we can basically establish a base case when n equals to 0, which basically means 1 plus x to the power of 0 is 1, but 1 can also be known as 1 times x to the power of 0, which matches the general description of the theorem. Are we doing okay so far establishing the base case of proof by induction? When n is 0, then 1 plus x to the power of 0 is the same thing as the summation of I going from 0 to 0, picking 0 out of 0 items times x to the power of 0. It's the same thing. It is actually on the whiteboard already. If you look at the whiteboard, this is our base case. Are there any questions about the base case? Now, normally, the base case is a very easy one to prove, okay, because you are talking about a specific case, so you can plug in actual numbers to establish the equality and say, yes, it is true for this case. The next one is called the step of induction. The induction step is a little bit trickier. What it says is you are going to assume, okay, and you say, if the theorem is true for case n minus 1, then it should also be true for case n. I have to prove that if it is true for case n minus 1, then it also has to be true for case n. Is that okay so far? And this is the step that is kind of confusing because, well, but how do we know it is true for case n minus 1? Well, we don't know in general, okay? We're just saying that if it is true for case n minus 1, then I have to prove it is true for case n. If I can establish that implication, then the proof by induction is all done. Because if you track back for any type of n, if this is true, okay, if this implication is true, then I can go from n to n minus 1. Then I can go from n minus 1 to n minus 2, n minus 2 to n minus 3, and eventually, if I keep going backwards, I will hit the base case, which is when n equals to 0. So that's why the induction step is so important, because it gives you a way to go all the way back to the base step, which is equivalent to this particular statement in the recursive version of factorial. It is basically saying, well, I'm not really quite sure whether factorial itself is going to work. Assuming f is working correctly, then I can rely on the factorial of n minus 1 to calculate the factorial of n. Same thing. Are we doing okay so far with the basic idea of why we have a step in proof by induction? So in this particular case, the step of proof by induction is to show this implication. If we start with something like this, which is basically saying the theorem is true up to n minus 1, I want to use this particular assumption and say if that is true, then it is also going to be automatically true that case n is also true. But what about case n is n plus 1? We don't care about n plus 1 at this point. We just want to go by 1. Okay, so we just want to connect case n minus 1 to case n. Are we doing okay so far? What we are really trying to prove when we're dealing with the step of this induction here. All right. So we'll just focus on, how do we go from here, given, assuming this is true, how can we establish this particular thing? So what we do is we start with this, okay? We just start with this part here and say, okay, let's see where we can go with this. And unfortunately, the formatting is off center a lot, and I can't pull it back to the other side. I wonder if I use the other browser, it would be better. Just hold on 1 second. Let me give it a try. I'm going to use Vincent's modded previewer, and then we'll just copy and paste it. Here it is. And for those of you who want to find out, how I type all of this stuff here, just out of curiosity, you can just right-click, show math as, type command, and then we just do a Control-A, Control-C, and then go to the previewer window and stick it here. It works out the same way. It's still kind of shifted all the way, but at least with this one I can move the horizontal scroll bar, so it's a lot better. Okay, so we'll look at it like this. Are there any questions about the first line, going from x plus 1 to the power of n to x plus 1 to the power of n minus 1 times just x plus 1. I'm just separating one of the n terms out on its own. That's all I'm saying. Any questions about this step? No questions. But it is a very important step. The importance of this step is I can now say, oh, but I know what is x plus 1 to the power of n minus 1 according to the assumption that the theorem is working all the way up to n minus 1. I know what it is, right? So when you look at the second term, okay, going from the first row, going from this part here to this part here, I am making use of the assumption that it does work up to case n minus 1. Okay. Are there any questions about this step? Because this is actually making use of that assumption, that it does work up to case n minus 1. No questions about this step? Okay. If you scroll all the way to the right-hand side, I actually put in the tags here to explain what that step is doing. So if you look at this row, it says by induction base. The base case of induction allows me to go from the first line to the second line. Are there any questions? Okay, well, if there are no questions, then I will ask you, how did I go from the second line, which is this one here, go on, to the third line, which is this one here? What did I do to go from the second line to the third line? The distributive law, okay? Because all I did was to say, oh, the first one will just multiply x to every single term, and then the second one, I'll just multiply everything by 1, which means I just keep it the way it is. So the only difference between the first summation term and the second summation term is this little plus 1 here. Because I'm just combining this x with the full summation term, so that each term is not x to the power of I, but x to the power of I plus 1. Are there any questions about how I went from the second line to the third line? No questions? Okay. So going from the third line to the fourth line. Okay. Going from the second line, the third line, which is this one here, to the fourth line, which is here, exactly what did I do? I didn't do anything about the second summation term, so don't look there. What happened to the first summation term? What did I change?
Starting from 1.
I shifted, right? So instead of going from, instead of having I to go from 0 to n minus 1, I have I going from 1 to n. Now, if I go from 1 to n, I have to make some adjustments, right? The adjustments that I'm making, I don't have to do anything about n minus 1 because n is not affected by the summation. So it's okay all by itself. But the I here needs to be adjusted because it used to be going from 0 to n minus 1. Now that I is going from 1 to n, this number, in order for this number to be the same as before, I have to subtract 1 from it. And that's why it is I minus 1 in this case. And and also over here, I was multiplying the combination by x to the power of I plus 1 when I was going from 0 to n minus 1. When I goes from 1 to n, I don't need that plus 1 anymore. I just need the I. So by playing with by playing with the limits of I and also the terms inside, I can quote unquote shift it by 1 and preserve exactly the same value. Are there any questions about this part? Now, if you just look at this line here, okay, without going any further, okay, can you kind of have a intuitive idea that, hey, I can see a little bit, not the entire thing, but I can see a little bit of Pascal's identity here. Okay, can you guys see a little bit of that? What is Pascal's identity? Let's go back to Pascal's identity first, and we'll see how these things are all connected. Okay, so we'll look at Pascal's identity, which is under probability distribution. And this over here. Okay, so here's Pascal's identity, which is this one here. This is Pascal's identity. And this is where we are at. Do you see how in the number of combinations, we have the same term as the number of items that we are choosing from? The number of items that we are choosing, one is I minus 1, and the other one is I. Okay, but we are not quite ready to put those two things together because the terms are not exactly agreeing, because with the first summation, we are going from x to the power of 1 to x to the power of n. With the second one, it is off by 1. We're going from x to the power of 0 to x to the power of n minus 1. So we have two n terms that do not have anything to match. So what we do is we separate those two terms out. Okay? So from the first summation, this term has no matching term from the second summation. So we have to kind of pull it out and say, hey, you have to stand on the side because you don't have a dance partner from the other side. Are we doing okay so far with that one? Okay. And then from the second term, we also have a loner who doesn't want to dance with anybody else. So we have to pull that guy aside and go like, well, you have to sit over here. But everybody else from the first term and everybody else from the second term they have a pair. So what we do is we pair them up. So in the middle, now we have I going from 1, not 0, to n minus 1 and not n, because we are taking the last term out of the first summation. We are taking the first term out of the second addition, but then the rest of the terms have matching x powers of x. And once you match up the powers of x, we can finally bring choosing I minus 1 out of n minus 1 and choosing I out of n minus 1, we can now finally bring these two together. Are there any questions about going from, let's see, 1, 2, 3, 4, 5, going from line 4 to line 5? Yep.
Yeah, so wait, why is the first item x to the n power?
Because it is the last term of the first summation. So if you look at this summation here, the very last one has I equal to n. So we have x to to the power of n here. And then we also have I being n. So this is n minus 1. And that's my n minus 1 is. We're just isolating the last term out of this summation into its own individual term so that everybody else can pair up. Because this one does not pair up. There's no one from the second summation here to pair up with this one, because no one from the second pair has x to the power of n.
Okay, and another question is,
Mhm.
if you're taking out the first, okay, never mind. I think I got it.
Okay. And this is the trickiest step because I'm actually doing, I guess, 3 things in one. Okay. The first one is to isolate the last term out of the first summation. The second one is to isolate the first term out of the second summation. And then the third one is to combine everybody else so that the coefficient coming from the first and the coefficient coming from the second cannot be added because they all have x to the power of 1 to x to the power of n minus 1. So that's how I can group all the terms together. But now we can see why Pascal's identity is actually important because it goes in here. So if you look at that term, it fits into the format of Pascal's identity, and we can just say, hey, we can just increase the number of items to n, and we'll choose I items out of that. Are there any questions about how I applied Pascal's identity? Yep, go ahead.
Different question, actually.
Yep, go ahead.
For the 0 choose 0,
Uh-huh.
the last piece.
Yep.
They're equivalent, but should they technically be n minus 1 choose 0?
You are correct. It is technically it's n minus 1. Yep, you're right. So let me go fix it first. Okay, so I'll fix it in the notes first. And am I looking at the right one? Not the right one. This one. Last one, 0, 0. Okay, so this one, and minus 1 is here. Good job. That's absolutely correct. Save display, and I'll fix it. This one here. And okay, 0, 0. Which is here. Minus 1. There we go. Thank you. So that would be the first term out of the second summation. Yep. Okay. All right. So now that we have this term here, actually that means the next row needs to be changed as well. Yeah, yep. This one needs to be changed. So I need to do a little bit more change. I apologize for the fixing here, but if I don't fix it now, I will probably forget. That's the problem. This is n minus 1, and then the next one is n. Okay, so let's get back to this part here. I apologize for the disruption, but is that okay now? I mean, is everybody still getting this part? Let me ask you then, how many ways can I choose n minus 1 item out of n minus 1 item? When the ordering is not important. Exactly 1. How many ways can I choose 0 things out of n minus 1 things? Exactly 1. Okay. So from here to the next row is really the other trick. That one of the not so obvious trick is to go from this one to the next row. Okay. So in the next row, which is 1, 2, 3, 4, 5, 6, still on the 6th line, I say, hey, choosing n minus 1 out of n minus 1 is the same as choosing n out of n, because they're all 1. Choosing 0 out of n minus 1 is the same as choosing 0 out of n, because they're both 1. So now I change the coefficient. Even though they are all just 1, and both of these are 1s as well, I'm just re-expressing it. Okay, I'm just re-expressing it. And then in the inside, I use Pascal's identity and combine these two terms into just choosing I out of n. Now the really cool part is we can see everyone is now choosing from n items. The first term on its own is choosing from n items. The summation term, everybody in the summation term is choosing from n items. The last term, which is on its own as well, is also choosing from n items. But when you look at how many we are choosing from n items, this one is choosing n out of n. This one starts with 1, but it ends with n minus 1. This one is just 0. Hey, I can now combine the whole thing into one single summation. So this really is if I have to pick one step that is the trickiest of this entire proof, it is going from line 5 to line 6. To basically re-express choosing n minus 1 out of n minus 1 to choosing n out of n. I would say that would be the most unobvious step. And the next one is easy. The next one is really just recombining everything into the summation of I going from, oh man, I made another mistake here. That's a 0 to n, okay, because that's just the theorem itself. And so the theorem is proven. Well, it's not proven yet. This is the step of induction. So now you have to combine the base case. So, okay, if I keep scrolling in the notes itself. There we go. So if I look at the notes here, so we have the base case, which is true when n equals to 0, and then we have the step, which is saying, knowing that case n minus 1 is true, we are now able to prove that case n is also true. Combining the base case and the step in induction, we now can come to the final conclusion that for all n as a natural number, this is true. And the black square at the end here is just another way to say QED. Are we doing okay so far with this proof? Other than the little mistakes, kind of sprinkled along the way. Yep. Not really, because I know some of you have photographic memory, and you can look up every single proof there is out there and memorize everything. And there's no point in doing that. I don't want you to waste your brain cells in memorizing a proof. So what I would usually do instead is, something that would involve the application of the knowledge. So you would probably have to reapply what you have learned in the test. But I'm not going to ask you to prove something, a theorem that is already well proven, and there are 20 gazillion ways to do it too. This is just one way to do it. Any other questions? Questions? Okay.
Can you explain that last step again?
The last step?
Yeah.
You mean the
I'm going
just this line here?
and she's and yeah. Very much.
You mean scroll up a little bit?
Yes.
When is the homework officially due?
The Tuesday after spring break. Okay, which part? This part? Okay. Let me stop the recorder first, because it's not going to be able to pick up any.